So up to now, we've talked about objects with mass, which were surrounded by a gravitational field. We then moved on to charged objects, or charged particles, which were surrounded by an electrical field. And now we're going to be moving on to magnetic objects, which of course are surrounded by a magnetic field. So what exactly is a magnetic object? Well, if we zoom down to a very small level, everything is made up of atoms. And atoms have a nucleus, and orbiting this nucleus are electrons in something called an orbital. And within these orbitals you have suborbitals. And these suborbitals are just basically regions surrounding the electron, where electrons, or regions surrounding the nucleus rather, where electrons can exist. And within these suborbitals, electrons can exist in pairs. So you have one electron and another electron. And so if we zoom in to one single orbital, we have a pair of electrons at most. We either have one singular electron or two. Cannot have more than two. And one of the properties of these electrons is called spin. So we have this spin property. And by convention, one of the electrons has to be spin up, usually the first one, and the second electron is spin down. And it's this spin property that creates a magnetic field. Now usually, since these electrons are paired, and one is spin up while the other is spin down, this pairing cancels out the magnetic field. They create magnetic fields in opposite directions, if you will, which cancels the magnetic field. And atoms where all the electrons are paired, so all electrons are paired, are called diamagnetic. But sometimes you do not have enough electrons to pair all of them. And so what you have is a single orbital with only one electron. So we're missing the second electron. By convention, this single electron is spin up. And so we do have a net magnetic field in this case, because this magnetic field created by this singular electron is not cancelled. So we do have a magnetic field, since it's not cancelled by another spin down electron. And so overall, when you have an object composed of many of these atoms, you have an overall net magnetic field. And these atoms, so non-paired, if you have at least one non-paired electron, these atoms are called paramagnetic. Usually though, when you have an object, so you can imagine some mass, these magnetic fields created by these atoms align in different directions. So if these vectors are directions of the magnetic fields, they align in different directions, and so overall you have no net magnetic field. But there are some special atoms which, when they align, influence each other and create regions called domains where all the magnetic fields are aligned in a single direction. And iron, nickel, and cobalt are some of these atoms. And what you call these atoms, which have this domain packing, they are called ferromagnetic. These are the atoms that compose your regular bar magnets, or the magnets that you see in stores. So this is what you think of when you think of a magnet. Of course, there are some lab procedures or some experiments that you can follow to turn paramagnetic materials into magnets, but the most usual materials that you use for your conventional magnet would be cobalt, iron, or nickel. Of course, these magnetic materials create magnetic fields or are surrounded by magnetic fields. And this magnetic field is denoted by an uppercase B, and it's a vector with units of Teslas, or T. Now, when we consider the magnetic field, or drawing a diagram of the magnetic field, if we compare it to the electrical field, in the electrical field we had field lines that went from a positive region, or started at a positive charge, and went all the way and ended at a negative charge. Now, in the case of magnetic fields, we don't really have field lines, but rather we have field loops. And the direction of these loops goes from a north pole all the way to a south pole, and then back from the south pole to the north pole inside the magnet. So this is on the outside and this is inside. So if you imagine a bar magnet, we have a north pole and we have a south pole. On the outside region of this magnet, we start our field line and go over to the south pole, and then inside the magnet we go from the south pole back to the north pole. And the same occurs on the other side. And of course, just like with electrical fields, the closer the field lines are, the stronger the field in that region of space. And there's no crossing of field lines because they represent the direction of a force, or a magnetic force, that a magnetic object would feel in this region of space. And so if two field lines cross, you'd simply draw the resultant instead. So if we were to complete this diagram, we'd get farther field lines the farther apart we are from the object, or from the bar magnet, and we'd simply go on. Now, this concept of loops, or having magnetic loops, is really important because it implies that all the magnetic field lines are connected for magnetic fields. And so in other words, we cannot have a north pole without a south pole. And a short way to say this is that there is no such thing as a magnetic monopole. So whereas in electrical fields we had a singular positive charge and we had a singular negative charge, in magnetic fields, if you imagine that we have a bar magnet with a north and south pole, and it has, let's just draw one field line for now. If I cut this magnet in half to get a north pole by itself and a south pole by itself, the field lines will stay intact, but instead they'll look something like this. And so what turns out to happen is that these two portions, or these two halves, also have a north and south pole and a north and south pole. So cutting a bar magnet to separate its poles simply gives us two smaller bar magnets. So in essence, there's no such thing as a north pole with field lines going out in all directions. And there's no such thing as a south pole with field lines coming in at all directions. These things do not exist as of right now. They have not been seen or observed experimentally. Now, something very interesting about these magnetic fields is that they're connected to electrical fields. Which we won't be getting into in this course. However, we will explore the relation of magnetic fields to moving charges. So any moving charge, so any charge q with a velocity v will generate a magnetic field. To understand the direction of this magnetic field, we use something called the right-hand rule. So for positive charges, suppose we have our positive charge and it's moving to the right. Then what you do to find the generated magnetic field is that you point your thumb in the direction of the velocity. So we point our thumb towards the velocity, the thumb of the right hand, of course. That's why it's called the right-hand rule. If you do this with your left hand, you're going to get the opposite direction. So you point your thumb in the direction of the velocity, and then you curl your fingers towards your palm. Or curl your fingers in the only direction that they will curl. Curl fingers towards palm. So if we have our positive charge going to the right, I take my right hand, point my thumb in the direction of the velocity, and I see that my fingers will curl outwards or towards me. So the direction of the magnetic field in this case is going to be in circles coming towards me. If this was a negative charge, so if we had a negative charge going in the same direction towards the right, I can also use the right hand rule. So I'll put my thumb in the direction of the velocity, my fingers will curl towards me once again, but since it's a negative charge, the magnetic field goes in the opposite direction. So it's going to go away from me. So another example, if we have a positive charge going downwards, we point our thumb in the downwards direction, and your fingers should curl once again away from you. Something like this. So if I can draw a diagram, we point our thumb in the downwards direction, and your fingers should curl around the velocity this way. Now, in most cases, we want to use these magnetic fields in a 3D plane. And so sometimes you're going to have a magnetic field coming out of the page and a magnetic field going into the page. The way we represent this on a 2D surface, if we have a magnetic field coming out of the page, So out of page. We draw it with a circle. So this is a magnetic field coming out of the page. If we have a magnetic field going into the page, so into page, then we draw it with an X. And the way you can remember this is imagining an air or an arrow with feathers at the back. So if it's coming towards you, all you see is this arrowhead, which is represented by a point. And if it's going away from you, you see these feathers at the back, which you can imagine to look like X's. Now another example of positive charges or moving charges is current, and more specifically conventional current. So we're imagining positive moving charges, because of course current is moving electrons, but when we talk about conventional current, we're talking about positive moving charges. So in the same way that we have a magnetic field that comes out of the page, we can also have current that comes out of the page, and it's also represented by a dot. So if we have current coming out of the page, represented by a dot, once again we can use our right hand rule. So if I point my thumb, my right hand's thumb, towards me or out of the page, then my fingers are going to curl towards the left, or in a counterclockwise motion, like this. And so the magnetic field around a wire connecting a current that's going outside of the page is a bunch of circles like so. And these are called concentric circles because they never cross, and essentially each one has a larger radius than the next. Of course, if I have a current going into the page, represented by an X, I can point my thumb into the page or away from me, and my fingers are going to curl in the opposite direction, or towards the right, or in a clockwise motion, like so. And that's all for the right hand rules for now. Well, actually, that was kind of a lie, because there's one more right hand rule that you should be aware of, but it's really an extension of the other right hand rules. So imagine we have a wire that's curled in a spiral, like so, and we run a current through this wire. So our current is also going to go in a spiral, like so. So it's going sort of into the page. Then we know that there's going to be a magnetic field created around this wire. But since all these wires are curled in such a way, these magnetic fields are going to interact, and we're going to make one bigger magnetic field, a larger magnetic field, which is the sum of all the smaller magnetic fields around these wires. To find the direction of this magnetic field, we curl our fingers. So curl our fingers in the direction of the spiral curls. And then your thumb is going to point in the direction of the north pole. And of course, this is for your right hand. So if we do this for the example we have here, we're going to curl our fingers away from us, or towards the page. And then we're going to see that our thumb points to the left. So our magnetic field looks something like this, where we have our north pole to the left and our south pole to the right. So if we curl our fingers towards the screen, we have our north pole to the left and our south pole to the right. We could also draw field lines if we want. So our field lines would look something like this once again. And essentially what we have here is a bar magnet that's created solely from running current. And this spiral wire is called a solenoid. Now, since we know that every single moving charge, so every moving charge generates a magnetic field. If this moving charge is moving within an external magnetic field, then the magnetic field that it generates is going to interact with this external magnetic field. So this field that it generates is going to interact with the external magnetic field. And what happens is the moving charge feels a force. The moving charge feels a force from external magnetic field. Now it's very important to note that just because a moving charge generates a magnetic field, it's not going to feel a force unless there's an external or another magnetic field so that the two fields can interact. So you have to have a charge within an external magnetic field. So if we can imagine a region of space where there's an inwards magnetic field, so that's going to be represented by a series of x's. Suppose we have a positive charge that is moving to the right within this inwards magnetic field. So we have our magnetic field and we have a moving charge. We can represent this in a series of 3D axes. So we have our field going inwards like this. We have a velocity of our charge to the right. And we have our positive charge at the origin. It turns out that the force or the magnetic force rather, will be specific. The magnetic force, which is denoted with an F sub B, is always perpendicular to both the velocity vector and the magnetic field vector. And so in this case, since the velocity is to the right and the magnetic field is inwards, we have two options. Our force can either be upwards, so that it forms a right angle with the magnetic field and a right angle with the velocity, or it could be downwards, which also forms a right angle with the magnetic field and the velocity. And the actual direction, up or down, depends on the charge. So if it's a positive charge, it's going to be in one direction. If it's a negative charge, it's going to be in the opposite direction. So it turns out for this example, the magnetic field force is going to be upwards. And the way we can write this mathematically is that F is equal to the charge, so in this case that's Q, multiplied by the vector for the velocity crossed by the vector for the magnetic field. This is called a cross product, which is a vector operation. And the cross product between any two vectors is always going to create a third vector, which is perpendicular to the two vectors that are being crossed. If you haven't done vectors, or if you haven't studied vectors and you're not familiar with this, it's okay, because you won't need it specifically for this course. What you do need to know is that the magnitude of this force is equal to Q times the magnitude of the velocity times the magnitude of the magnetic field times the sine of the angle between them. So if we have our velocity vector and we have our magnetic field vector, then the angle between them is what we call theta. In most cases, theta is going to be 90 degrees. And if it's 90 degrees, then sine of 90 degrees simply reduces to 1. So you don't need to worry about it. Now to actually find the direction, we have two more right-hand rules. So I'll erase this to make more room. So both right-hand rules work. The first of which is general for all cross products. So our right-hand rules, well, they're both general to all cross products, but the more general one. We point our fingers towards the first vector being crossed. So in this case, that's going to be the velocity vector. So we point our fingers towards the velocity vector. And then we curl our fingers in the shortest direction to the second vector being crossed, and that's going to be the magnetic field vector. So we curl our fingers towards the magnetic field vector. So in this case, we point our fingers with our right hand towards the velocity vector. And then you'll see that the natural direction that you want to curl towards is going to be the shortest direction. So we can curl either this way or we can curl this way. The shorter direction is curling inwards towards the magnetic field vector. So if we curl this way, then our thumb is going to be pointed upwards, and that is the direction of the field. So the thumb, or that's the direction of the force rather. So the thumb points in direction of the force. Now the second right-hand rule, which most people prefer, so we'll just erase this. The second right-hand rule is to point your fingers. This is going to be the opposite. So we're going to point fingers towards the magnetic field. So we're going to point our fingers towards the magnetic field. And then we're going to point our thumb in the direction of the velocity. And in this case, for a positive charge, both of these apply for positive charges. So we point our thumb in the direction of the velocity. Then our palm is going to push towards the direction of the force. So if you point your fingers towards the magnetic field and your thumb towards the velocity, your palm should be pointing upwards. And so that's going to be the direction of the force. So palm pushes towards the force. And most people prefer this because while in the first method you could curl your fingers in the wrong way, for example, maybe you chose to curl your fingers in the opposite direction, your thumb would point downwards and you'd get the wrong answer. In this case, all you have to do is point your fingers in the direction of the magnetic field and your thumb in the direction of the velocity, and your palm is automatically going to push towards the direction of the force for a positive charge. Now let's say this charge was negative. So it was a negative charge that was moving within the field. Then I would do the same thing. I'd point my fingers towards the magnetic field, and then my thumb would point in the direction of the velocity. Again, my palm is going to push upwards, but since it's a negative charge, I do the opposite. And so my force is going to be downwards. Now if we do another example, suppose we have a negative charge, but it's moving to the left through the field. Then what we can do is we'll point our fingers once again in the direction of the magnetic field. Now we have to point our thumb to the left because it has to be pointing in the direction of the velocity. So I have to flip over my hand. My thumb is going to point to the left. Now my hand is backwards, and so my palm is going to be pushing downwards. But we need to remember that this is a negative charge. It's a negative charge, so since my palm is pushing downwards, the force that a negative charge feels is going to be upwards. And so if this was a positive charge moving to the left, the force that it would feel would be downwards. Now, two things to note from our force equation. So we have FB is equal to QVB sine theta in magnitude. So one thing is that we know that sine of 0 degrees and sine of 180 degrees are both equal to 0. This means is that if we have a magnetic field moving in some direction, then we have a charge, positive or negative, moving parallel to this magnetic field. So either with the magnetic field or in the opposite direction of the magnetic field. If it's moving with the magnetic field, the angle between the velocity vector and the field vector is 0 degrees. If it's moving in the opposite direction, the angle is 180 degrees. In both these cases, then our force is going to be equal to the charge times the velocity times the field times sine of 0 or sine of 180. And so the force is going to be equal to 0 newtons. In other words, a charge moving parallel to field experiences no force. The other thing to note is that if we isolate for B in this equation, we have B is equal to the force divided by QV sine of theta. And so we know that B has units of Teslas. We can find what Teslas are equal to since we know the units for all these quantities. F is equal or has units of newtons. Q has units of coulombs. Velocity has units of meters per second. And sine theta is simply a number, so it has no units. So one acceptable answer for the units of a Tesla are newtons times seconds divided by coulomb meters. But if you remember from grade 11, a coulomb per second is simply describing some quantity of charge per some amount of time, which is exactly how we define current. And current has units of amps. And so more commonly, you'll see that a Tesla is expressed as newtons per amp meter. Now to solidify this entire lesson, we have an example. So we have a charged particle that enters an inwards magnetic field of 3 Teslas, moving 5.5 times 10 to the 6 meters per second to the right, at an angle of 60 degrees with respect to the field. The particle, we're told, is experiencing a force of 8 times 10 to the negative 13 newtons downwards. And if that's the case, we want to find the charge on our particle. So since we have a angle that is not equal to 90 degrees, we're probably going to want to use axes for this problem rather than sticking to 2D. So we have our 3D axes. So I'll draw my velocity as my reference. So it's going to be moving to the right. My magnetic field is inwards. So if it were directly inwards at perpendicular to the velocity, we draw it something like this. But we're told that it's 60 degrees with respect to the velocity. and so it has to be closer to the velocity, so that we have to decrease the angle. So it's going to be something like this, where this is an angle theta, and theta is equal to 60 degrees. And we're told that the particle, which we don't know if it's positive or negative, so Q, and we don't know its charge, is experiencing a force that is downwards, a downwards force. And note that this is still perpendicular to both the velocity and the magnetic field. I can draw a right angle like that and a right angle like that. So FB is downwards, and it's equal to 8 times 10 to the negative 13 newtons. My magnetic field is equal to 3 teslas, and the velocity is equal to 5.5 times 10 to the 6 meters per second. So the first thing I'm going to want to do is find the sign of my charge. So we'll use our right hand rule. In this case, we point our fingers. I'll use the second right hand rule. So we'll point our fingers in the direction of the magnetic field. And then our thumb is going to point in the direction of the velocity. And in this case, my palm is going to be pointing upwards. And so a positive charge would feel a force upwards, which means that since our charge is feeling a force downwards, it has to be a negative charge. So our charge in this case is negatively charged, such that it experiences a force downwards. Now we took care of the sign. So anywhere we have an equation, we're not going to use the sign anymore, because we already took care of that information. We're only going to use the magnitude. So if we write our equation for the force, FB is equal to Q V cross B, which is equal to, in magnitude, because that's all we care about now, Q V B, and then sine theta, and we can isolate for Q to find its magnitude. So Q is equal to FB divided by V B sine theta. And now we can substitute. So we have FB is equal to 8 times 10 to the negative 13 newtons divided by our velocity, which is 5.5, times 10 to the 6 meters per second, times our magnetic field, which is 3 teslas, times the angle between the field and the velocity, which is 60 degrees. And if you plug this into your calculator, you'll get an answer of Q equals 1.65 times 10 to the negative 19 coulombs. But do not forget that we found that Q has to be negative for this to be possible. And so our final answer for Q is a negative 1.65 times 10 to the negative 19 coulombs. And if we want to do some unit analysis, what we have is newtons divided by meters per second times teslas. And we saw earlier that a Tesla is simply a Newton per amp second, or amp meter rather. And so this meters is going to cancel with that meters. This Newton is going to be cancelled with this Newton. So we have is 1 over 1 divided by seconds times amps, which is equal to an amp second. But an amp is equal to coulombs per second times seconds equals coulombs, which makes sense.